Hey y'all, this is Amelia. Welcome again to Heat and Mass Transfer. Today we're doing problem 3.39. That is, problem 39, chapter 3. We're going to do this thing. It's kind of a long one today. It's discussing this little heat thing here. You've got your inner diameter. You've got some heat source on this inner inside. You've got this insulation shell. You've got um, temperature at the inner radius, temperature at the outer radius, a couple of radii, and we're just going to be today figuring out, based on whatever types of radiation, or not radiation, sorry, whatever types of heat transfer that we're dealing with today, how much heat are we going to lose? How do we predict the outer shell temperature after the insulation, et cetera, et cetera. So this is going to be a steam pipe. It's got an outer diameter of 0.12 meters. With calcium silicate insulation. I hope you guys can read my handwriting. If you can't, that's okay. I will try and read through as much as I can. There's a couple of parts. So for part A, we are given a thickness of insulation of 20 millimeters, which is 0.02 meters. The temperature at the inside surface is given at 800 Kelvin, and the temperature at the outside surface is given at 490 Kelvin. These are currently labeled as TS, 1 and TS, 2. Later on, they will change to T1 and T2 because I didn't want to write commas all the time. So just as a forewarning, these will be T1 and T2. For parts B and C, we only know the inside temperature as 800 Kelvin. We know that the outside will be exposed to airflow with a bulk fluid temperature of 25 degrees Celsius and a convection coefficient of 25 watts per meter squared Kelvin. We also know the outside, which is R2, so that's T2, will be exposed to large surroundings. So we're going to assume it's a small object in a large enclosure, and those will have the same temperature as the bulk fluid, and that's going to be 25 degrees Celsius. We are also given the surface emissivity of the calcium silicate insulation is epsilon equals 0.8. What we're asked to find in part A, we're asked to find Q prime, which is the heat loss rate in per unit length of pipe, so that's watts per meter. We're find in part B, we're asked to compute and plot the temperature distribution in the insulation as a function of the dimensionless radial coordinate r minus r1 divided by r2 minus r1, where r1 is 0.06 meters and r2 varies between 0.06 and 0.2 meters. That sounds like a headache, I know. Basically, what this is doing, what they're asking for here is they're instead of saying, okay, we've got a pipe that is, we've got all these dimensions. And instead of trying to predict, oh, at insulation thickness 0.634 meters or 0.0634 meters or whatever the number is going to be, predict it there and then predict it at this different point. We're going to try and we're going to try and make this all dimensionless. So we are going to make it a sort of, think of it like a percentage value on a scale from 0 to 1. So we are going to go, instead of saying, okay, at radius point, if we have R2 as an example, because R2 ranges from R1 to whatever thickness, instead of saying, oh, we're going to do it at, R1 is 0.06 and R2 is 0.012, I don't know, 0.12. We're going to say, okay, instead, we're just going to say it is all uh, a fraction. So whatever radius we have that we know is between R1 and R2, we're going to subtract R1, which is the smaller radius, and we're going to divide that by the largest possible fraction, which is going to be R2 and R1. So regardless of what R2 is, we're going to be expressing this as a fraction of the distance between R1 and R2. So instead of saying, 0.14, which could be somewhere in here, we don't know, we're just going to say this is 0, this is 1, it's somewhere in the middle. Part C, we're asked to compute and plot the rate of heat loss as a function of insulation thickness for 0 to R2 minus R1 is 0.14 meters. So this is fairly similar, but it's not non-dimensional. Instead, we are just going to be saying, oh, I don't much care how thick or how large the steam pipe is. all I care about is how much insulation we're putting on it. And this could be used for like if you've got a steam pipe that's 0.12 meters and a steam pipe that's, I don't know, 30, that's a crazy number, but 30 meters or whatever. That's probably not a thing. Um, you can say, well, instead of saying our, steam pipe diameter is 0.06 meters and our insulation or our steam pipe radius is 0.06 meters and our steam pipe our insulation radius is, you know, zero point 0.2 meters, we can be like we put 0.14 meters of insulation on this pipe, and then you can say, oh, on the other one we also put 0.14 meters of insulation. So that's what we're doing with that one. Some assumptions. We're assuming it's inside. We don't have any radiative input from external flux. So there's no sunlight, there's no heat lamps. We're not, shining a spotlight at this thing. It's a small body in a large enclosure, so we're going to have radiation based on not where it's not going to be black body radiation. Our system is radially symmetrical and has no variation in losses with theta. So in that case, basically, all of your losses around your pipe in all directions are the same. We're not going to say, oh, at this point it's this much losses, but on this corner it's a lot less or a lot more. It's also the same. The pipe wall stores negligible energy. This is kind of also saying, that we're not really including the pipe wall in these calculations. We're basically just it's not really relevant. Um, it's not, a very important assumption. It's just primarily to say we're not dealing with the pipe wall. We don't care what the inside diameter is. No phase change within the system. So it's a steam pipe, but once you involve phase change and then you have to deal with latent heat and all this other stuff, no, thank you. We're just gonna say no phase change, no heat, no like no, we're reducing the complexity as much as possible. This is not a steam pipe that turns, this is not a steam pipe that turns into a water pipe. No. Conduction is one dimensional in the R direction. So conduction is again outwardly, it's like radial. We're not dealing with any variations in theta. The system is steady state. So actually this is I guess is another thing in terms of like the system is steady state. So the temperature is not changing with time. Temperature is purely a function of radius. We're not venting enough heat to significantly change the steam or, the insulation. We have a negligible thermal resistance in the pipe wall. That's another way of saying we're not dealing with pipe walls today, just the insulation. And actually, because they gave us the ODU, this is actually not a necessary assumption. This is an example of an assumption you don't need to make right now. But moving on. We're assuming that all material properties are constant and anisotropic. Constant just meaning that like they don't vary with time, they don't vary with temperature. I don't want to deal with like an insulation that says, oh, so by the way, when I'm at this temperature, I get this much worse at insulating. No, we're not assuming that. Anisotropic, meaning that all of the properties are the same going in all directions. So if I have a cube of insulation, it's not gonna insulate better in the X direction than it would in the Y direction than it would in the X direction. It doesn't really change. One final one, this one will be slightly relevant later. We're going to assume that the thermal conductivity of the material can be approximated with linear interpolation. This is me saying I don't want to do math. So for solutions, we've got a couple of relevant equations here. We've got our heat equation. This has already been simplified. This is the cylindrical heat equation for steady state because you can see there's no change in temperature with time, and it's also one-dimensional in the radial direction. We are also saying the temperature distribution. Actually, this equation is not relevant for this problem. We are saying also the heat rate. Again, this is your like conduction, your conduction law over time for a cylinder. Here's the, calculus version, which I don't recall if we'll be using that today. Thermal resistance, another one. It's just again, thermal resistance of a cylinder with two radii. Not all of these will be relevant or used today. They're just kind of our equation bank of, hey, I need to look at something. I'm going to take a look at these. So first, solution. Part A, remember they're asking us for, heat rate per heat loss per meter of piping. So we've got our equation of just overall heat lost. If we take one prime, we take off the L. That's literally the same thing, but I took out the L. This is your heat rate per unit length. So if we just divided that by L, it takes out the L. This is your heat rate per unit length. Delta T, the inside we know is 800, the outside we know is 490 in terms of Kelvin. So we're going to assume the conduction is from the inside to the outside. So we're going to say delta T from hot to cold is T1 minus T2, that's 310 Kelvin. They gave us R1, they gave us R2 as they gave us the thickness of the insulation so that we know that. K, this is actually out of Appendix A, Table A3 of a different textbook, so it's don't quote this for Bergman and Levine 2017. But we have our watts per meter Kelvin thermal conductivity of our insulation varying between 0.075 and 0.104 watts per meter Kelvin at 530 to 750 Kelvin. So again, this is going to linearly interpolate that. I know you guys have taken thermo at this point. So that's just going to be, first one plus slope times temperature change. And that is going to be, we're going to get a thermal conductivity of 0.09. If we just plug and chug this, double check our units, 2 pi doesn't really have units, but we have watts per meter Kelvin in this K. We've got Kelvin here. This is a natural log of a ratio, so there's no units here, and that's going to get us 610 watts per meter. Moving on to part B, it's going to get a little more complicated. Here's our heat diffusion equation. Simplified already. Steady state, one direction, no heat generation. That's another important assumption that I did not list up above, but we're assuming that no heat is generated within this insulation. We are going to assume that it's a closed system with no heat anyway, here's that assumption listed out. No heat generation in the control volume, which if you can read my chicken scratch, there's a dashed line here and a dashed line here. So the control volume is just going to be this insulation. If we do a closed system energy balance, we're going to have no heat generation and steady state. So energy in is equal to energy out. Energy in, we'll get there. That's a later problem. But we do know what is given in terms of our outside losses. We've got radiative losses and we've got convective losses. And so we know our E out is going to be our convection plus our radiation. But important note here for parts B and C, they don't give us T2, so we have to figure out what T2 is. So just for starters, let's use our closed system energy balance. We do know, since we're not doing, we do know that whatever heat is, because it's steady state, whatever heat is lost to this convection and this radiation is going to be replaced by heat coming in from conduction. So we can say we've got this like our conduction law from T1 to T2, and then we've got our radiation and convection from T2 to the bulk fluid temp and the surrounding temperature. If we do a little bit of algebra, divide out by the 2 pi and rearrange the terms, we've got this long, funky equation that's got, your K over ln ratio, and then you've got your T's and your other stuff. But you notice we can move all of the T2 terms to this side. So if we factor out the T2 and then isolate it on this side and then divide it back under, we get T2 as a function of R2, and it's this whole mess over here. We can also say, if we remember a couple of things, this is just an explanation briefly of H sub R. If you guys recall from radiation, it's just that H sub r. If you do some algebra over here, some factoring, you're going to H sub r is equal to emissivity, Boltzmann constant, and a few just some, if you what's it called? Anyway, this is HR. It's an important thing. We're going to assume that HR gets fixed at the information given to us in part A. So we're going to assume it's just a ballpark guess. It's a ballpark guess because we don't have enough information to really fix it. So instead of having a really complicated equation that references itself a zillion times, we're just going to say it's fixed. So now we have T2. It's a mess, but it's there, and we can plug in whatever R we want. We can get there. So now that we have T2, we have to look for TR prime, where R prime is that dimensionless radius that they were asking for earlier. So if we remember here, the heat diffusion equation for radial one-dimensional steady state no heat generation, it's this. A little bit of basic calc. We get rid of that radius here. We just multiply it across, but again, it's a 0 on this side, so it's gone. Move over the dr and integrate. Or actually, integrate both sides with respect to r. Same deal, even if this is written a little weirdly. You're going to end up with your r dt dr on this side, and this is going to be a constant because we integrated from 0. Then we're going to move the r to the other side and not double integral, but like integrate both sides again. So we get temperature as a function of radius is going to be C1 ln of r plus C2. And for this, we need two boundary conditions. We don't need any initial conditions because it's steady state, so it's not changing with time, but we need two boundary conditions because we've got two constants here that we need to figure out. We know that at that the temperature at radius 1, the internal radius, is going to be T1. They gave us that. T at R2 is going to be T2. Again, they didn't give us a specific R, but they gave us a range of values that they wanted us to look at for R. So this is basically just a function describing, T2 at whatever R we choose. To continue this solution, again, this is a quick recap because I was changing pages. So if we non-dimensionalize it now, we've got our R prime is equal to R minus R1 divided by R2 minus R1. So it's expressing the fraction of the distance between R1 and R2 that we've actually passed through at that point. It's linear interpolation again. If you think about it that way, it might help you, not sure. But what we do now is we're going to say, okay, we've got R prime, but our function is a function of R. So how do we change R prime to R? How do we separate this little boy over here from, the rest of the function? If we multiply up this R2 minus R1 and then add the R1, we get R as a function of R prime. And then we can substitute that into our temperature function. And I know this looks like a mess. Bear with me. The reason this is important is because now we can say our boundary conditions are at r prime equals 0 and r prime equals 1. So it's a bit of a headache, but it is important for it's an important concept for other things. If we take these two boundary conditions, we say T1 and we plug in, R1, so we get C1 ln R1 plus C2. And we're actually not plugging that into this one. Up here, we're actually plugging it into this one because you see if we plug in R prime equals 0, this whole shebang goes away and you're left with the R1. So it's the same deal. And then we do the classic, I'm going to subtract these two equations from each other. Get T1 minus T2 is equal to C1 ln R1 over R2. This is actually ln R1 minus ln R2, but because of log rules, you can collapse it into each other. And then from there, you can divide over the ln ratio and get your C1. From this first boundary condition, we're going to do something similar. We're going to say C2 is equal to T1 minus C1 ln of R1. That's just this equation that's just this equation right here. We just have this T1, we subtracted over the C1 ln R1 to leave ourselves the C2. We're going to plug in the C1 that we got, so we have T of R is equal to T of R prime. We're going to plug both of those things into this T of R prime. So we're going to say C1, which is this T1 minus T2 over the ln ratio, times ln of this mass, plus C2, which is the T1 minus C1 ln R1. We can then, combine like terms and factor, and we'll end up with T1 minus T2 divided by the ln ratio times the ln of all of this, uh, this number divided by R1, because again, it's two ln's subtracted, and you can log roll that. And then you've got this T1 over here at the end. I've got this arrow here just denoting that, remember that T2 is a function of R2. Next, we are going to be, sorry, one moment. Next, we are going to be doing a heat loss per unit thickness of insulation as a function of insulation thickness. So if we've got our Q prime, which is what we're looking for, we can set it up as, because we know that it's steady state, we can say that the energy lost here per unit length, we're going to represent that as our, going to represent that with our the losses from the convection and the radiation. It's the same as the conduction, but it's a little bit more, I don't know. It's more set in stone because they gave us the temperature or the values for H and such. Apologies for the screen jiggle. I bumped my laptop. So there's that, but we want it as a function of thickness. So we're going to do the same thing as earlier. We're going to make a new variable that's thickness equals R2 minus R1. Again, it's the difference between the inner and the two radii. So we're going to do, hey, R2 is T plus R1. We're going to substitute it into this function of R2. There is no parentheses here, but I should emphasize that this is a function of R2. And then we're going to substitute that in, and oh, look, we've got, Q of T, Q prime of thickness is all of this stuff. It's the same thing as here above. We've just substituted in all of these values. So what we're going to do from here is I'm going to demonstrate these three equations in this MATLAB code, because remember, in the problem statement, it didn't just say calculate, it said calculate and plot. So this is, pretty standard. We've got our radius vector, our vector of like radius points. We've got our R1, our R2, minimum temperature, and the temperature well, it's not necessarily the minimum temperature. It's just the temperature we're going to use to calculate the radiative coefficient, or yeah, HR. We've got our other values here. This one is 25, gets converted to Kelvin, because when you're in heat transfer, you usually want to deal with Kelvin. Because it's an absolute scale. If you really want to use Rankine, I'm not stopping you, but I don't recommend it. Been there, done that, didn't like it. You can also these are just our constants. We've got our emissivity of our insulation and our Boltzmann constant. We've got H sub R, which is that we calculated earlier, which is going to be here somewhere. One moment. Nope, that's backwards. H sub R is going to be, as we calculated, right there. And then we're going to have define our thickness and our R prime variables. And then for every R2, for every time we're doing a different R2, and this is going to be starting at 0.06 and incrementing at 0.005, we're going to do those long equations. This one for every R is also going to calculate the temperature profile for every R prime. So it's a nested for loop. And then we're going to plot all of these things on their own charts. If I run this real quick, I believe in you, computer. We've got our three figures. Here in the front, we've got our temperature profile as a function of R prime. So from 0 to 1, we've got this one here is going to be the one with the least insulation. And then as you see, as we add more insulation, it gets, so the curve becomes more and more of more like an inverse exponential, or like a negative exponential kind of it goes from linear to like very less linear. You can also see that after a certain point, you stop really getting great improvements. So it's a good way of being like, hey, how much insulation can we put on here versus how much insulation do we need to put on here? Next, we've got this one. It's our Q prime heat loss per unit length watts per meter based on insulation thickness. So that's another curve. And then over here, we've got our outer surface temperature, T2, as a function of insulation thickness. Yeah, that's it. Thank you guys.